Hi, hello everyone. I'm Maira CANAL. I'm a kernel developer at ighlighting. I'm usually around the DRM subsystem. I'm the kernel maintainer of the Raspberry Pi GPU driver, so that's what I usually do. But I was involved in the Rust for Linux project a couple of time ago. It's great to be here this year. I hope we can enjoy a bit of, make this time a bit productive right now. So first, the agenda. While I was drafting this talk, I was thinking how I could structure it in a productive way because we have been hearing a lot about Rust in the last few years. I mean, we had a talk yesterday about Rust, and I think that at this point we all know about the great things that Rust can do. We all heard about the memory features, procedural macros, and all that, so I won't be discussing Rust in a technical way. I decided actually to go in a more historical way. Like, there's a sort of an interesting thing about how we perceive events as humans. Because we are living through events in real time, it's very easy to lose sight of what's really going on. Because, I mean, we have been watching the Rust for Linux project evolve in real time. And we have been hearing about it in conference talks, maybe LWN news, maybe in NRFC, in the mailing lists. But due to the fast flow of information that we live in our day-to-day lives, and also some isolation that exists between kernel subsystems. I mean, the kernel is huge, so it's very normal not to be completely aware of what's going on in other subsystems. I think it's okay not to be completely updated on what's going on in the DRM subsystem. So, and also, even if you are updated, sometimes it's really hard to tell noise from trend because sometimes you only heard about a very heated discussion that happened on the mailing list about Rust, or you saw in a blog post some maintainers, arguing, this sort of stuff. But today I decided to take a step back and try to review what has been going on in the DRM subsystem in the last few years. By reviewing those relevant events, I think we can try to discuss, answer some questions at the end of the review, like why Rust seems to be so suitable for GPU drivers, and why Rust seems to have this great success in the DRM subsystem. As a disclaimer, I'll be focusing only in GPU drivers today, so I won't be talking about all the other great things that the Rust for Linux project did in other subsystems. I know that the situation is a bit different in other subsystems. Other drivers are being developed in other subsystems, so today I'll be talking only about the DRM. So I will start this talk with a brief timeline of what happened in the last few years in the DRM subsystem. So I gathered here what my personal selection of important events in the recent years for the Rust for Linux project in the DRM subsystem, but also I added two important points for the Rust for Linux history as a whole. First, the first RFC, which happened in the beginning of 2021, and almost 2 years later, we have the initial Rust support being released in Linux 6.1. This first version only had very minimal Rust support, enabling some experimentation and such, but it was not like a driver or something very complete. But I think that we can say that from this point on, things kind of moved quite fast, especially considering the size of the kernel project. The kernel project is a huge project. It has a lot of years of history behind it. And when we have such a project with so many people, so many stakeholders, sometimes it's hard to make things move forward. And I think that the Rust for Linux project ended up moving quite fast. For us to, jump into some points in this timeline, I divided this timeline into a couple of sections. So I'm going to start it with what I called the Asahi era. From what I could recall, and also I ended up doing a review from blog posts and the mailing list. In the end of this presentation, it has an appendix with all the references from what I collected during this research. And I think it was an era really characterized by some enthusiasm and some uncertainty from my perspective. Enthusiasm because it was the first fully functional driver written in Rust for a hardware, like a commercial hardware. And some uncertainty because if you see in the timeline, actually the public announcement for the Asahi driver happened even before the Rust support in mainline. So it means that the Asahi driver started to be developed in Rust even before, Rust being mainline, which makes it even more fascinating, and it shows that the Asahi project really bet on Rust's success. And for those who are unfamiliar with it and don't know what the Asahi driver is a reverse engineered driver for Apple M1 and M2 GPUs across a couple of firmware versions. It was a result of a truly pioneering work did by Asahi Lina between 2022 and 2023. And it was the first GPU driver written in Rust. And this is a pretty big achievement because not only it was reverse engineered, but it was written in Rust, which means that she had to write all the safe abstractions for several DRM structures. And the DRM has a lot of structures. And it was really impressive at that point because to this day, we still use those safe abstractions. I mean, most of them, even in the first RFC, got like great positive feedback, and several of them are being upstreamed right now or were already upstreamed as part of the Nova/TRI effort. And as I mentioned, I believe that at this point, the general feeling was like enthusiasm and expectation of a quick merge. As you can see, I took this quote from the RFC. The expectation was to get this upstream for 6.6. I mean, we are in 6.18 right now. And sometimes we were like thinking that this would really move really fast. But as I said, the kernel is a huge project, and sometimes we need to reach some consensus in the community before making those big changes. But the RFC was a full package in a way because it had the safe abstractions and also the driver, which avoided that famous chicken and egg problem with the Rust abstractions. The Asahi driver to this day is not upstreamed yet, and it's maintained out of tree. However, some of Lina's abstractions are reaching upstream due to other drivers. And well, the next section that I selected was some pushback that happened in the community. After this first moment of enthusiasm, I would say that Rust kind of cooled down a bit in the DRM after some resistance in a patch set involving C changes. And I think that at this point, this was like in the middle of 2023, the community haven't reached yet consensus about how much C changes could be done in order just to make safe abstractions sometimes cleaner, easier to, structure, or even functional, as we are going to see, Especially, I believe that this friction around the DRM scheduler ended up being an important point, important event in the timeline, because it was a moment that the Rust conversation kind of vanished from the DRM mailing list. I mean, you didn't saw it anymore. And also, it demarked a hiatus in the Asahi driver in upstream. And the DRM scheduler series that caused this pushback was a 3-series patch with some documentation and about the DRM scheduler trying to, set some expectations about the inner workings of the scheduler, and also some fixes for lifetime issues. And for those who are completely unfamiliar of what lifetimes is in Rust we have this idea of a lifetime semantic, so I'm trying to wrap this idea very quickly just to make sure that everybody's in the same page. When we are thinking about making a safe abstraction from C to Rust, we need to understand the lifetime semantics of that C object. So when we have like this C object, like the DRM scheduler, we need to understand its lifetime. What does this mean? It means that we need to understand who owns it, I mean, when it was allocated, who owns it, when it's going to be freed, who frees it, and also how long is this pointer valid in time. And this can be a bit complicated when we have like many pointers, alias, things are mutating, and we also need to understand if this is thread safe or not. And as you can see, the idea here is like having a mental model of what that thing, of what that C struct is doing in the code, its whole lifetime. And after we have this mental model, we can just, encode this model into Rust semantics. I mentioned, I added a list of some things that we can, let's say, transpile these concepts like lifetimes, drop, phantom data. But the general idea is just having this mental model of the lifetime of this C object and then turn this into Rust semantics. And finally, document some safety expectations. So as you may notice, you need to have a very clear vision of the object that you are modeling. And we need to make sure that its behavior is completely bounded and protected against undefined behavior. And well, the DRM scheduler looks like this. I mean, does it work? Yes, it works, at least most of the times. And does it have a set of well-established rules? Yes, it has. Some partially documented, some very well documented, and some are probably documented in a 2010 mailing list discussion. So the point is that the DRM scheduler can be really tricky. And it's not really trivial to deal with the scheduler. And some adjustments needed to be made in the C side to make things go forward. Otherwise, we are not able to make this mental model very clear. So in the end, I believe that this pushback that happened in the mailing list, because it ended up that we weren't able to reach consensus at that moment about the scheduler, made things look like things weren't going forward for the DRMs, for the Rust for Linux project, and probably gave some bad press for the kernel community due to many blog posts and social media things that were generated from it. But I think that in the end, different people ended up joining the Rust for Linux project, and we started to work and try different approaches to collaborate with the community and try to get consensus to merge code, which I think that leads us to the Nova era. From what I could understand, for me this is a maturity phase for the Rust drivers, because some groundwork had already been done, landing some foundational abstractions in the Rust core, and we now are able to, have two new drivers coming in, which were Nova and RVKMS. Well, again, making sure that everybody's in the same page. Nova is a is a driver for GSP-based NVIDIA GPUs that was developed by Red Hat and NVIDIA devs. Actually, some of them are in the audience right now. I listed a couple of them here in the slides, and I'm not going to say their names because I'm probably going to mispronounce it, but I mean, thanks a lot for working on this. And it is intended to become the successor of Nouveau at some point and in the mainline. And why they decided to write a new driver? From the documentation of the Nova project, we can see that Nouveau was, for most of its part at least, was designed in the pre-GSP era. By the way, GSP is GPU system processor. And Nouveau was written around 2009, and its authors back then had to reverse engineer a lot of the hardware. This means that the code base right now, it can be a bit tricky to maintain. And it makes sense now that a lot of the hardware internals were moved to the GSP firmware to simply write a new driver that can be much cleaner. I mean, a lot of that hardware abstraction layer ended up being moved from the driver to the GSP firmware. Now the driver needs only to interact with the firmware. So we can write something that's more cleaner and maintainable. So it makes a lot of sense to start from the scratch instead of maintaining the pre-GSP code with the GSP GPUs. Also, around the same time, the RVKMS project was announced. The RVKMS is a port of the virtual KMS driver. The virtual KMS driver is called VKMS. We should note that the Asahi driver, although it was fully written in Rust, it's only the GFX part. The display part was written in C. So in order to write the RVKMS driver, all the KMS safe abstractions needed to be written. And also, the DRM and KMS are in the same subsystem, but the structures that they deal with are completely different. The DRM part is more like GFX stuff, and KMS is essentially display. So they had to write all the safe abstractions from the scratch. And Ludpol sent a couple of RFCs introducing both the driver and the KMS abstractions. However, the driver is not upstreamed yet. On the other hand, the Nova project is advancing quite fast. I mean, a stub driver for Nova was already merged in mainline. And I believe that Nova is quite a fascinating case that we have in the DRM, especially due to the strategy that they chose to interact with the community and how to merge the driver. Actually, if you see at this point, those are all files that are already upstreamed, and I took this from Linux 6.17. So, like, at this moment, we already have at least this core, a stub driver in mainline, so it's already merged. And I think that the part that was really smart from the developers was that instead of waiting for the driver to be fully completed, which can take a lot of time, the Nova developers worked with the community to make sure that the project grew with upstream. For example, they promoted a Rust topic in the DRM tree in order to, create a community around that topic and make sure that everybody, to create like a base to work with Rust drivers for DRM. This is really smart because when you are developing like a huge driver like this, only in downstream, and the Rust for Linux project evolving quite fast, this will result in several rebases that we are going to have to do, and changes in API, all this stuff. And when you create this possibility for the community to interact and have a common basis, we ended up like fostering community engagement around it, which is really smart. And now the driver is in mainline, and they keep developing the driver already in mainline, which is also great because you don't need to worry about the constant rebases, and you also have this community that is growing around it. And finally, to the current moment, I extracted this quote from Daniel Almeida, who is also in the audience, because I saw that this talk in FOSDEN, like earlier this year, in February. It was a Rust for Linux talk from Miguel, and I remember this quote because I saw it like February 1st, and for me this quote sums up the year perfectly. I mean, 2025 is the year that we are seeing this huge progress being made. Daniel probably knew a thing or two of what was about to happen, but it stuck in my mind, this quote. And I think that this sums up perfectly. Daniel itself, with Alice announced the TRI driver in June, and it's a Rust-based driver for CSF-based ARM Mali GPUs, and the Strub driver is already queued for 6.18. Also, several abstractions from Linux itself are being revamped, improved, and merged at this point. And more functionality is being added to Nova and TRI. So again, these drivers are in mainline, but they keep evolving. So I think that also this answered the question, can I run like NVK at this moment with TRI in my ROC 5B? Yeah, not quite there yet. But these drivers, I mean, there are a lot of workforce around it to make sure to develop them and make sure that they are like the standard in the next few years. And also some old points of friction are being addressed, like the DRM scheduler. I think that recently we have been seeing multiple efforts to improve the DRM scheduler with documentation, correction of undefined behavior, fixing some use after free issues and more. And also we are seeing some effort to merge the fair DRM scheduler algorithm, which is based on the original CFS algorithm from the Linux scheduler. And this has the great potential to simplify some of the DRM scheduler inner workings, and it would replace the current FIFO and round-robin algorithms that we have in the DRM scheduler, and it would really reduce a lot of code. However, all those improvements might not yet be enough to, comply to all the, let's say, rules, quote unquote, that Rust needs. So Rust developers are currently developing a brand new scheduler fully in Rust. And well, after this retrospective, we can jump into the two questions that I mentioned earlier. I think that a fair question at this point is why Rust seems to be so perfect to write GPU drivers. I mean, we are seeing so many being developed recently. Like, what Rust do that C doesn't? And I mean, of course, Rust has many benefits that you probably already know. GPU drivers can benefit a lot from Rust ownership model, lifetime model, and also because like GPUs are highly concurrently and asynchronous, so they can really benefit from all that. And also, it's great the way that you can model your API in a way to catch some logic bugs at compile time, etc. But I mean, again, why GPU drivers are special? What make them like need a modern language, let's say? And when I was thinking about this, I noticed one particular thing about the GPU architecture recently. One important point about the GPU architecture nowadays is that we are evolving in a direction to have more dedicated coprocessors inside of it. For newer GPUs, the idea is that the host CPU, it's going to send commands, let's say mailboxes, something like that, to the GPU through a coprocessor via firmware, basically. This communication is happening via firmware. And this means that a lot of stuff that used to happen in our host CPU, like scheduling, power management, context switching, security, all of that is moving from our host CPU to the coprocessor in the GPU. So you can clearly see this trend at the moment, because we can see NVIDIA has the GSP, which is like a RISC-V core inside the GPU. Apple also have this coprocessor, which is like an ARM 64 core running a real-time proprietary OS from Apple. You also have the ARM Mali with the CSF, and AMD GPUs have so many coprocessors that I wasn't able to enumerate all them here. And so far, this seems completely unrelated to Rust, But this trend implies that we are progressively offloading the hardware abstraction layer, all those things that deal with scheduler and all that, from the driver to the firmware. And this usually means unstable firmware ABIs. Because, firmwares usually are proprietary. And usually also they have unstable ABIs. And, this is not a problem for hardware manufacturers because you can simply just bundle the firmware together with the driver and ship to the client. It doesn't, if you make some changes to the ABI, you change the driver as well, you bundle them together and it's fine. However, this is not possible in the kernel because once we support a firmware version, we need to keep supporting it. And we cannot just, remove support from one version to another. And well, how we deal with different ABI versions in C? Usually this means a lot of function duplication, file duplication, and structure duplication. In the slide, you can see some structs that I extracted from the AMD GPU driver, and you can see that it's basically the same firmware header, but with different versions. And you have like a lot of them. I just picked 2 examples, but there are a lot of those in the AMD GPU driver. And you see all these versions that they change very little between versions, the struct itself. And of course, this also means that we have one function to deal with each one of those versions. So you have like pretty similar functions. They are mostly identical, change one thing or two, and you're just repeating the same code over and over. The other option would be to make some complicated code generation with C macros, but C macros are very limited. It's kind of hard to make very fancy macro thinking C, and usually it's not that readable. But in Rust, you can do something as simple as this. This code was extracted from the Asahi driver. And as you can see, you can just, of course, there's some code behind it, but you can use macros to just define the fields for each version. And the idea here, for example, let's say the counter field, which is the second one. The idea here is that the firmware, the counter field, only exists if the firmware is greater than v13.0b4. And if the firmware is less than this version, the counter won't exist. And when we use the Rust analyzer to expand the macros, you can imagine how powerful this can be. Because if you noticed, the counter field only exists in the versions that we defined before with the macro. So this is the expansion that I did with the Rust analyzer. This is not code that you are going to see in your code base. This is like when we expand macros in C, and this is super powerful because, look, the code here is very clear, is very readable. The semantics are very, obvious. You can just read, okay, the version, it's going to exist when the version is greater than v13. And you can do the same thing for GPU generations. For example, you can see the registers field. It only exists for G14X, I think, greater than G14X. And you can see here that all the other versions use the job parameters. And when you have the GPU version, which is G14X, you have the register field, which is really useful because sometimes from one generation to another, you have like some changes in how jobs are submitted or things like that. So I think that as programmers, we can only imagine how powerful this can be for like several applications. And finally, why did Rust succeeded in the DRM? Like what makes the DRM subsystem so special? And I think that it worked first because the DRM maintainers were willing to bet on success of Rust. I would even say that they weren't like saying that Rust was going to succeed or not, but they were willing to at least give it a try. And also, there's a interesting thing about the DRM, because the DRM operates in the group maintainership model, which means that we have several committers and responsibilities are a bit shared. So the DRM, this model really eases the load on top of the maintainer, because the maintainer can share the responsibility, for example, of Rust review, which was a topic that was brought several times. The maintainer can share this responsibility of reviewing and maintaining it with other committers and contributors. And also with such a model, the workload ends up being spread around between committers and maintainers and developers. And I believe this had an impact to make the process of adopting Rust much more smoother in the DRM subsystem. And finally, I think that the idea of merging very sizable stub drivers is really nice, because in the end, the community ends up growing around these drivers. And this ends up decreasing the delta between the development branch and the upstream branch. And also, it helps to, breed some interest around it, because, people are seeing those things in mainline is much easier than, go around many repositories looking for downstream projects. And finally, is Rust the new standard in the DRM? I think that for new drivers, we can say probably, maybe, because for recent drivers, it is a trend that we are seeing. Like, everything that is being written from the scratch in the DRM is now written in Rust. And I would say that probably if someone is going to start to write a driver today, it's probably going to be in Rust. So yes, that was what I had for today. Any questions?
Hi, thanks for the talk. I was just curious about the Asahi project. You mentioned that the DRM scheduler changes that were required on the C side kind of blocked them from upstreaming the driver. Is that correct? One of the things.
I mean, I'm not Asahi Linux. I'm not a Asahi contributor, so I cannot say for sure, this was the reason. I mean, I cannot say for sure, but it really demarked a point in which we saw a hiatus. If you see, the appendix here, I don't know, you can see that, for example, the last patch that was sent was this one, the DRM scheduler documentation. So then you have something like only in 2025. No, yeah, nothing more.
Yeah, so and then later you mentioned that the DRM scheduler was rewritten in Rust.
Yeah, it's currently being rewritten, but
yeah, so I was wondering, why wasn't the DRM scheduler written in Rust in the first place? Why were they trying to use, use the C bindings? Because there's two ways you can do it, right? And I'm kind of struggling with that myself, actually, because, given a library or something that you want to write, you have the option of calling into the C one with bindings or writing the whole thing in Rust. And that's not always possible, because sometimes on the C side you have interaction with hardware and other subsystems. So you can't always rewrite everything in Rust. But yeah, I don't know that much about the DRM scheduler, so it sounds like if it's now being completely written in Rust, it's kind of an independent thing that doesn't have those problems. So I was wondering, why wasn't it written in Rust in the first place, if that's what was a problem for the Asahi project, or one of the problems?
I think the first thing, like the DRM scheduler is used for all GPU drivers that you see nowadays. So it's a very common piece of the DRM structures. And as was mentioned yesterday, the idea is to build the safe abstractions around them, not rewrite code in the kernel. This code is well established, is used by multiple drivers. If you have a Linux laptop, you're probably using the DRM scheduler. So it's not something that you can just, start from the scratch and say, oh, we are abandoning the DRM infrastructure. In the end, I think that this, and also by that point, I'm not sure if the DRM maintainer at that point was willing to just accept another DRM scheduler written in Rust. The DRM maintainers changed in the last few years. So
well, I just talked to some of them, and one of the drawbacks of writing it in Rust is that now when you have C drivers that don't want to use, like whoever's working on the new DRM scheduler in Rust, they will not be able to use it. So it kind of creates like, that's one of the reasons why you want to make it such that it's something that everybody can use, so you can continuously improve it. But maybe that'll change when when people call into Rust code from C, which is something possible. So I don't know, but yeah. Somebody else had a question?
So I think it's worth saying that the DRM scheduler being written in Rust is not really, like, it's not a direct replacement of the existing DRM scheduler. The existing DRM scheduler is targeted at cases where you actually need to do scheduling on the CPU. And the new thing is I think they're going to call it the job manager, and that one is going to be targeted at cases where the GPU has firmware that does the scheduling and you just give it all the jobs. And so it's not really a replacement, it's just a new component.
yeah, that's the thing as well, because like if you have things like the V3D, the Raspberry Pi GPU, we still schedule things in the CPU. That's why we have like scheduling algorithms. But if you offload this to coprocessors, as I mentioned in many cases, for example, I think the Intel Xe uses this case, you don't need those scheduling algorithms anymore. And then the scheduler is just this big blob of code with algorithms and very complicated stuff that you don't use at all.
I just want to say one thing, by the way. Apparently, whoever initially asked the question said that if you do something in Rust, then the C drivers do not get to benefit from it. And I just want to correct that, because that's definitely not the case. So everything you do in Rust, you can expose a C API for the C drivers to use it. There's a small process where you sort of have to build this API and sort of do a small translation layer between the two languages. But like, I had a whole talk about this actually. Once you actually write a Rust function, it gets compiled into machine code. Whoever's calling it doesn't really know or care, right? So long as he uses the C API, you can call Rust functions from C drivers just fine. So from that point of view, it's definitely not a problem. And I was also going to say what Alice has already said, that it's a new component. So it's not just a rewrite of what we had over there. And I also think that back then there was, Rust was this new thing. The discussion got a little bit heated. And now, given that we're writing this new component, which is not a direct replacement, I think that also helped the argument. Like, we're not trying to get around people. We're writing a new component because we have an actual need for this new component. It's not because we had a disagreement with someone. Hopefully that helps answer the question as well. More questions?
I wanted to know what the the connection between the DRM work you're doing in the kernel and all the user space side in Mesa is like, and whether Mesa, which those are mostly the same developers, I'm guessing, whether Mesa has seen some Rust usage as well.
Yeah, I mean, the kernel, we have the kernel space, right? And we only expose like the UAPI to Mesa, the user space. And the kernel space only exposes the UAPI, and it's like using any UAPI. We just call ioctls from Mesa. But as far as I understand, it's completely transparent to Mesa if this is a C driver or a Rust driver, because it's just a UAPI call. And in the Mesa side, I know that there is the NAC project for the NVIDIA compiler that is being developed for NVK. Okay, that's it. Thanks.